Hi, my name is Jacob Roel and my topic is predicting patient length of stay and identifying the factors influencing length of stay. Introduction. Hospitals play an important role in providing health to society. However, they face some challenges. Hospitals have limited available resources such as beds and doctors. Therefore, it is essential they manage their resources efficiently. A solution to this is to use length of stay, or LOS, which is the number of days between admission and discharge. Monitoring LOS could help hospitals plan their resources and reduce costs. Accurate LOS predictions enable hospitals to plan accordingly. Also, identifying the factors leading to extended LOS allows hospitals to focus on the important factors. Human estimations of LOS are not always possible and generally not accurate. Many studies have predicted LOS using machine learning classification models such as a neural network. Based on the literature, 3 models were selected for comparison: decision tree, neural network, and random forest. Feature importance has been determined using feature selection together with correlation measures and directly from the models. Aims and motivation. The aims are to find a subset of important features which can predict LOS. Additionally, we try to improve the prediction of LOS using a subset of features instead of all available features. The motivation behind this is that some features may have high variance and can even worsen the model and the prediction due to overfitting. The subset of features will enable hospitals to prioritize acquiring the most important features. Methods. How was it done? Methods overview. This diagram describes the overview of the methods, in which we will describe it in more detail in the next few slides. We start off with a raw patient data set in which we select 100,000 samples. We then pre-process the data and use feature selection to come up with a subset of features. We then compare the subset of features to the original features, and we use this red box to train and test the data. We use the hyperparameters, the 5-fold cross-validation, together with 3 classification models to train the data. We then use the testing data to obtain the results, and we compare the models. Dataset description. This dataset was provided by the New York State Department of Health, and it is freely available. There are no personal information features, therefore there are no privacy concerns. All the records are from 2015. We sampled 100,000 records and there are 36 features in the dataset, together with one target label, the length of stay, which is measured in days. A list of features are summarized here. We pre-processed the data by removing unimportant features and samples. We removed irrelevant features such as patient disposition. We removed this feature as this feature tells us where the patient was discharged to, for example, home, but this information would only be available to us after the patient leaves the hospital, but we want to predict the LOS for patients on arrival. Similarly, payment features we also couldn't predict because this was only available after a patient was discharged, and discharge year was only the year 2015, so this is redundant to include this feature. We also removed features with missing values and also samples with missing values. We also removed equivalent features, for example, APR severity of illness code and APR severity of illness descriptions are the same features just with different representations. This left us with from 36 features to 19. We then used feature encoding, for example, label encoding, to convert the categorical features to numerical values as models need numerical values, and then we scaled the data. The target feature LOS is a continuous feature by nature, as it could range from 1 day to infinity technically. We therefore discretized LOS by converting the continuous stays to a binary classification. So if the stay was less than 3 days, then we converted it to class 0, being a short stay, and if it was more than 3 days, then we converted it to class 1 and we considered it to be a long stay. This also combated outliers, as if you have outliers, it will just be part of either the very big class or the small class, but no real outliers were detected. We then balance the data and we use undersampling to undersample the majority class. After cleaning the data, both the short and long stays had 44,298 samples. Feature selection. From the 19 features, we removed more features to obtain a subset of the original features. We implemented feature selection using Pearson correlation. Pearson correlation measures the linear relationship between two features. If two features are correlated, then we remove the less correlated feature with LOS. We also removed features which are not correlated with LOS. And we chose a 0.3 threshold for similar features and a 0.07 threshold for a feature which was not similar or not correlated at all with LOS. These thresholds were chosen based on the tuning of the validation dataset. Training and tuning the hyperparameters. This dataset was divided into training and testing sets in a ratio of 80:20 for the original dataset with the 19 features and a subset of features. A 5-fold cross-validation with the grid search was used to train and tune each model with its optimized hyperparameters. We also produced the correlation thresholds as we described earlier using this technique. We experimented with different hyperparameters to tune each of the 3 models, and the hyperparameters that gave the highest accuracy on the validation data was selected for each model. We then used the test data for reporting. The optimized hyperparameters for all models were implemented for both the original and the subset of features. For example, this table shows the decision tree of hyperparameters. So the criterion had a value of Gini for the original and a value of Gini for the subset of features. Similarly, the max depth was 14 for the original dataset and 18 for the subset, and the minimum sample split was 129 for the original dataset and 78 for the subset of features. Obviously, these numbers and values were trained to optimize each model. A similar method we used for the neural network and the random forest hyperparameters. Results. Most patients in this study were between 50 to 69 years old. As we can see from this graph, older patients experienced longer LOS. As we can see that 70 or older had the longest LOS stay. The average length of stay was 5.5 days, and the most common stay or mode was 3 days. The severity of a patient's illness was highly correlated with the duration of length of stay. As we can see from the graph, that extreme severity was on average 12 days, compared to minor severity at about 2 days. The feature importance for the original features are ranked in this graph for decision tree in red and the random forest in green. We can see clearly that APR severity of illness is ranked as the highest feature, especially by the decision tree, and then APR MDC description and etc. And then below we can see gender, ethnicity, and other features were not ranked too highly as important by these algorithms. Subset of important features was reduced from 19 to only 4 features, with APR severity of illness again being ranked the highest, and then APR drug description and MDC description coming next. Interestingly, emergency department indicator is not rated that high, but it came up ahead of other features, which were technically associated or correlated with LOS, but the reason they were not selected is because those other features were associated with these 3 features, and this emergency department was not associated with these 3 features. This table summarizes the model performances using accuracy, F1 score, and area under the curve, or AUC, for the original and subset of features using the 3 models. We can see that the original and subset of features obtained similar results across all measures, and in some instances the decision tree even outperformed the original features when using the subset. So for example, over here, the decision tree obtained 75.35% using the subset, while it only obtained 73.66% for the original features, showing that subset can sometimes even perform the original data features. But in most cases, the neural network and random forest obtain better results using the original features compared to the subset of features. And our predictions are acceptable, as some results and some studies have achieved better and some studies have achieved worse results than ours. Discussion. The subset and original features produced similar performances on all models using accuracy, F1 score, and area under the curve measures. Therefore, the subset was able to predict length of stay without all the original features. Even though features such as age was correlated with length of stay, they were not part of the subset of important features. For those type of features, most or all of the information was contained in other features such as APR severity of illness. Therefore, keeping both features was redundant. Demographics such as gender and ethnicity and race was not important features, which is consistent with other research. Limitations and future work. All models were tested on New York State Hospital patients only, therefore the results could be biased towards these hospitals. Future work can be done using a different set of features and evaluate if the subset of features can even outperform the original features. Additional work can also be done by not including the APR and CCS features, as they were generated using computer classification models, and these features also happen to be the most important features. Conclusion. All three models obtain acceptable performances, meaning that they can all be used for length of stay predictions. However, the random forest did achieve better predictions than the other two. The subset of features was reduced from 19 to 4 features, with similar performance obtained using the subset and the original features. Therefore, hospitals should try to collect these important features: APR severity of illness, emergency department indicator, the drug description and APR MDC description, to train it with a model, and they can use it to plan accordingly and reduce hospital costs. Thank you very much.